Hello everyone. My name is Vaibhav, and today we are going to discuss the topic complexity of counting. So, what we are concerned with here is that how do we define complexity classes for problems which involve counting, and after we define such complexity classes, we will see how they relate to the complexity classes that we have already discussed in the course earlier, and how are they different. We are going to see that. So before we begin, let us just see what different types of problems are there, and what is the relation between them. So as we have seen a lot in the course, uh, which was based around decision problems, we have defined several complexity classes like P, NP, and so on, which are basically complexity classes which are associated with decision problems. So the one way to think about decision problems is like a map between a string and 0 to 1. So we can think like the input being a string, a Turing machine outputs whether it is accepting or not. So the basically deciding problems are mapping from a string to 0 to 1. So we have defined several complexity classes regarding these problems, and we have seen we have basically seen the hardness of problems and characterized them into several classes. So but we can define a general type of problems which are called as function problems, which are computational problems where uh, we where there is a single input and a single output. So it is also a map from a string to another string. So we can think of these kind of problems where a Turing machine accepts an input string and also gives an output string. So basically we imagine a Turing machine which can also write an output. So these type of problems are called as function problems. So a function problem P can also be described in the form of a relation, because we are concerned with two strings over here which are the input and output. We can characterize them as a relation R, which is a tuple of two strings. So a set of tuples of two strings. So R here is a subset of sigma star into sigma star. So here R contains the set, R is a set of all the elements where each element is an input string and the respective output string. So these are the general types of problems, and decision problems are a subset of such problems, because 0 and 1 are also string, right? So decision problems are just a subset of such function problems. So next what we are going to see is a different type of problem which are known as counting problems. So they are a subset of function problems also, and the difference here is they take a string as input and the output a natural number. So basically they give a number as an output. So even they are also uh, writing an output to a specific input string. So but here the output string has a specific meaning. So here these type of problems are where we are concerned with the number of accepting paths of the non-deterministic Turing machine which is deciding the problem. So here when you input a string to a non-deterministic Turing machine, you expect it to write an output giving us the number which is the number of accepting paths for that Turing machine. So we can think of many problems which are counting problems, and some of the problems which we will discuss uh, in this part is where we can see how we can find a complexity for those type of problems, and we can define how hard such problems are. So complexity problems are very useful in many areas of mathematics and uh, various other fields. So some of the examples are like enumerative combinatorics, right? So where you find basically are uh, finding number of combinations of a specific property, and although in such areas you can write a mathematical formula for finding whatever you're trying to. So if, for example, if you are trying to find the number of ways of arranging 5 balls, then you have a formula for it, a simple mathematical formula. So it is solvable in that sense. But as we can see uh, ahead, that a lot of natural counting problems are not easy to solve, and they do not have a simple mathematical formula for solving them. So let's see an example of one of the counting problems. So here what we are going to see is a graph reliability problem. So a graph reliability problem is where we are given a directed graph of n nodes, and we are told that each node has a fail probability with 1 by 2. So a node fails with a probability of half, and what we are told to compute is the probability that the node 1 has a path to n. So we can think of different ways using probability theory to come up with a probability which will calculate the failure probability, and we can minus it with the total probability, and we'll probably get the success for the node 1 to have a path to n. But instead of going through that route, we can think of it as a counting problem. So how do we think of it as a counting problem is, let's say we have a, a machine which gives us the answer for a counting problem for this graph reliability problem. So what we can find out is the number of subgraphs which has a path from node 1 to n. So basically we get the number of solutions for this graph. So once you have that, you can multiply that with 1 by 2 power n. So this will give you the probability of having a path from node 1 to n, because these the number of subgraphs in which node 1 has a path to n is the total number of accepting solutions, and 2 power n is the total number of uh, subgraphs uh, in the given graph. So we to find the probability of uh, the correct solution of getting a path from node 1 to n is basically number of accepting solutions divided by total number of solutions. So that is how you get this formula. So basically what we saw here is we converted this problem into a counting problem. So now let's see. So as we have discussed a little while before, that counting problems arise in diverse fields such as statistical estimation, statistical physics, network design, and counting problems are also studied in a field of mathematics called enumerative combinatorics, right? So basically where we try to obtain a closed form mathematical expression for counting problems. One more example of a counting problem is the number of spanning trees in a graph, and as we know that that can be done by uh, basically finding a simple determinant computation. So these are an examples where we have a specific mathematical expression to find the number of solutions, but in general, many natural counting problems uh, are not reducible to simple mathematical expressions, and they are much harder to compute. So now let us define FP. So FP is a class which is associated with function problems. So as we know that P and NP and other such complexity classes are associated with decision problems. In a similar way, FP is a class which is associated with function problems, so which take input as a string and give output as a string. So FNP can be thought of as a function class analog of NP. So in that, the solutions of FNP problems can be efficiently verified but not necessarily efficiently found. So just like in NP where you can easily verify a solution, but it is much harder to find a solution, FNP is a class where for a given FP you can verify the solution efficiently, but it is not easy to find the solution. So FP is also another class which is an analog of class P, and which consists of function problems whose solutions can be found in polynomial time. So you can find all the solutions in polynomial time. So these are very direct and related in a similar fashion. Now let us start with defining the first complexity class for a counting problem. So let us uh, start with the complexity class hash p. So hash p is a complexity class which is concerned with problems which involve counting. So before we begin doing that, let us first rewind and recall that we have already studied in the course, which is called as a configuration graph. So let us recall this thing because this is needed in order to define, and we'll use it later as well. So if you take a Turing machine M, uh, which is given an input X, so as we know, we have a transition table for a Turing machine, and we have an input tape and a working tape, right? So, and for every input symbol, we have a transition diagram which basically changes the configuration of the Turing machine tape. So, and we have discussed that we can draw a graph for such transitions and the whole possibilities of transitions. So here, configuration graph is a graph with the first node being the initial state, or initial configuration of the Turing machine M, and the neighbor of this node are all the configurations which can be reached from the initial state on an input. So we are considering a non-deterministic Turing machine here. So a single input on a configuration can have multiple branches. It can take any of the root. So here we see that this graph GMX is a configuration graph where each of the node is a configuration of the Turing machine. A configuration, as we know, is a combination of the memory of the tape and the position of the head of the pointer. So it describes the state of the Turing machine completely, and on the action of an input uh, based on the transition table, it moves to another configuration. So we get a tree structure here, and here we are denoting these green nodes as the accepting nodes. So uh, at some point in this configuration graph, we may find a node which is an accepting node or which is an accepting configuration. So that is when the computation ends and we know whether the problem is solved or not. So let's define f as a counting function for the above configuration graph. So what is a counting function? Counting function is uh, a function which counts the number of paths for a configuration graph which end up in an accepting node. So in the above graph that we have here, f of x is 4 because as we can see we have 3 accepting states here, and the number of paths to reach these accepting states from the initial state or the initial configuration is 4. So this is called as a counting function. And so how is counting problems related to hash p? So as we define hash p here, all functions f such that f of x, f which being a counting function, is equal to the number of accepting paths in the configuration graph G of a polynomial time non-deterministic Turing machine M on input x. So this is an important definition, and it might be misleading uh, if not given attention here, because we are specifying a polynomial time non-deterministic machine M. So we have to be very clear when we define this class, because we might misinterpret it. So let us again go through it. It's all functions f such that f of x, meaning on an input x, the computing function gives us the number of accepting paths in the configuration graph G of a given polynomial time non-deterministic Turing machine M on input x. So we have to be clear here that the polynomial restriction here is with respect to the non-deterministic Turing machine M, such that its accepting paths must be polynomial with respect to x, and it doesn't restrict the counting function f. It doesn't have to be polynomial in time. So here when we define this complexity class hash p, we are not concerned with saying whether this problems in this class are computable in a polynomial time or not. We are not concerned with the time it takes for problems in this class. What we are concerned here is with the accepting paths that it calculates for a given non-deterministic Turing machine must be polynomial time on input x. So as we can see here, so let's take this configuration graph here, and so a computing function computes the number of accepting paths for this graph, and the only restriction here is that the length of this path, of the accepting path, must be polynomial with respect to x. So the length of this accepting path can't be exponential, it has to be polynomial. But whereas the computing function itself, which computes the number of such accepting paths, doesn't have any restriction as such. So this is the definition of the complexity class hash p. Now Let us move on to, okay, so let's see, uh, in an NP decision problem, we have the question whether there exists a solution, right? So we are uh, concerned with, in a decision problem, we are concerned with is if there is a solution or not. Does a specific problem has a solution or not? And given a valid certificate or a valid solution, we can check if it is correct or not. So we can think of it in a way that we are only concerned with the question whether a solution exists or not, and we are not concerned with the number of solutions it has. We So if we know that we have a solution for it, then we can say it is decidable. So to uh, so here we study hash p, a complexity class which does this, which is concerned with finding out the number of solutions. And so here again we can define hash p in terms of a relation. So let's consider R as a relation which is a subset of sigma star and sigma star, and so hash p here would be defined as mapping from a string to natural number n. So here hash r uh, is describing uh, the counting problem here. So for all x which belongs to sigma star, so all the strings x, for all of this we define hash r as the number of this set where which has y such that x comma y belongs to R. So if this relation R has an element xy, so an input string x and an output string y, then this y is considered as part of hash R, and we calculate the number of such elements in this. So basically we are not, what we are doing is uh, so if we think of R as a function problem where it is a set of tuples where the first string is the input string and the second string is the output string, and this tuple is part of R only if uh, the input is a mapping is gives the specific output, so only then it's part of the R. So here we are checking all y's, all outputs y, which is part of the relation, meaning which is an defined input and output for some function problem, and basically the number of such outputs we are calculating, or the number of solutions that we are calculating, gives us the uh, number n, which is the hash r here. So uh, so this is basically defining hash p in terms of a relation. So we move on to uh, let's say f which belongs to hash p, so a computing function which is uh, in hash p. So how do we define it? How do we know whether a function f is in hash p? So f is in hash p if f is equal to can be written as a hash r hash if f can be written as a relation hash r. So for a relation R, so as we are concerned with uh, the number of output, the correct output for R, so R has to be a polytime verifiable, as we have already defined it here in the definition. We have to make sure that the relation R, which represents the function problem, it has to be polytime verifiable, meaning all the accepting states, so accepting paths for such uh, function problems must be polynomial in size. So uh, so two conditions for this R is, so if a tuple xy being input string and output string belongs to R, then the size of R is less than or equal to some polynomial function of the size of x. So as we have again stated before, it's the same point here. uh, the length of y must be less than or equal to some polynomial of the length of x. And the other pointer here is, for all xy belonging to sigma star, meaning all the strings x and y, any input string or any output string, m of xy should be 1 if and only if x comma y belong to R. So basically we are just defining here uh, R as a function problem. So it contains only the tuples x, y. If we have a Turing machine M which takes these two and gives 1. So it's like a polytime verifier where x is the input and y is the certificate, and we get 1 because it is accepting the certificate and it is a valid solution with respect to x. So these are the two conditions for the relation R. Now, as we have defined the hash p, now let us move on to how do we characterize the complexity of the problems in hash p, and how do we relate it to the complexity classes that we already know. So here, to do that, we need to look into two problems which will help us do it. So let us so the two problems that we are going to look in detail here is hash sat and hash cycle. So using these two, we can try to define the hardness of the problems in hash p, and we will see if we can find a correlation between these problems and the decision problems that we know. So let's start with hash sat. Uh, so hash sat is a counting problem which is analogous to the satisfiability problem that we have already studied, and we know that satisfiability is an NP complete problem, and it is NP hard, and if we are able to solve it uh, in polynomial time, then all the problems in NP are uh, are solvable in polynomial time, and then P becomes equal to NP. So let's see how the uh, counting problem and analogous of satisfiability behave. Is it also hash p complete? And let's look into that. So here we see satisfiability problem. Again, let us refresh what it means. It is the given a boolean function phi, we need to uh, tell whether the given boolean function phi has a valid assignment. So satisfiability is a decision problem, and So the question we are asking here is phi satisfiable, and we can model this question into, is there an accepting path for phi? So if we have a Turing machine for phi, uh, a configuration graph of phi, then if that configuration graph has an accepting path, then we can answer if psi is satisfiable. So again we can model this question again into a more general one, where is the number of accepting paths for phi greater than 0. So we are just stating the same question but in a different way here. So as we can see that if we get to know that the number of accepting paths for phi is greater than 0, then we know that phi is satisfiable, and if we get to know that it is not greater than 0, then we know that it is not satisfiable. So uh, it's the basic so it's the same question modeled in a different manner. So let us define what is hash sat, which is a counting analogous to sat. So what we ask here is, in how many different ways phi is satisfiable. So this can be modeled into a question again, what is the number of accepting paths for phi? So if we find the number of accepting paths for phi, then we know that so many assignments are also there for such phi. As we can see here, uh, the middle uh, part of the question is missing, because this is the difference between these types of problems. Here this is not about deciding something, whereas in SAT it is all about deciding a specific thing. So is there an accepting path for phi? So this is a deciding thing, it gives yes or no. Here we can't, there is no deciding uh, part to it. So now as we can see here, so hash p problem must be at least as hard as the corresponding entry problem. So we can see that if we are able to answer this question, then we can easily answer this. So if we know the number of accepting paths for phi, we can tell whether it is greater than or 0, greater than 0 or not. So hash p problem must be at least as hard as corresponding NP problem. And if it's easy to count answers, then it must be easy to tell whether there are any answers at all. So let us define hash p completeness. So a function f is said to be hash p complete if it is in hash p and every g which belongs to hash p is in fp of f. So here what we are saying is, for a function f to be hash p complete, first of all it has to be in hash p, and then every other function g which is there in hash p must be polynomial time reducible to f. So here fp of f here means a function problem which uses f as an oracle. So let's say we have an oracle for f, an oracle which computes f, then we can apply a function problem, or a polytime. Sorry, we are not concerned with polynomial time here, we are just concerned about uh, mapping of a string to a string. So we can convert that output of the oracle f into a problem of g. So this is nothing but, as we see here, for all g which belongs to hash p, g is polynomial time reducible to f. Now we will show here that HashSat is HashP complete. So in a way we are going to show HashP is a subset of FP HashSat, meaning all the problems. So FP HashSat is a class where all the problems can be function problem reducible using a HashSat oracle. So if we have an oracle for HashSat which gives the output for HashSat, meaning it gives the output for the number of assignments for phi, then we can compute any problem in HashP. So that is how we show HashSat is NP complete, because all the problems can be reduced to HashSat. So for that we need to first look into Cook-Levin theorem. Let us revise what we had learned earlier. Uh, so again here what we have is a non-deterministic Turing machine, and we have a configuration for that Turing machine uh, for a specific input x. Now as we have seen that uh, we can convert this configuration graph into a Boolean function. So, and this can be done in polynomial time. So this, we use this fact to show that satisfiability problem is NP complete. Now what we will do here is, for any non-Turing machine, any non-deterministic Turing machine and input word, we construct a Boolean formula in polynomial time where the Boolean formula is satisfiable if and only if the non-deterministic Turing machine would accept the input word. So here, yeah, as we have already seen that if this configuration graph has an accepting path, then the corresponding Boolean formula has an assignment, a valid assignment. So that is what we had seen in the Cook-Levin theorem. Now we need to define a property called parsimonious. uh, just a second. Okay, so parsimonious is a property which states that a reduction maintains the number of solutions for the transformed input. So one important thing, fact that we are going to use now to prove that HashSat is HashP complete is that this reduction, the Levin reduction which we used in the Cook-Levin theorem, is parsimonious, meaning the number of solutions for the number of accepting paths for a configuration graph gives us the Boolean formula which has the same number of valid assignments. So if we have if we have 4 accepting paths in this configuration graph, then the corresponding Boolean formula also has 4 valid assignments. So this property is known as parsimonious. It basically maintains the number of solutions for the transformed input. So we use this fact to prove now that HashSat is HashP complete. So let's consider a HashSat oracle, meaning an abstract machine which will compute HashSat problem and give us the output. If we have a HashSat oracle, we can use it to we can use it in a box where we take the input for SAT and we provide it to HashSat oracle, and we get the number of satisfying assignments for phi. So Now let us take uh, an input for f which belongs to the hash p class, and when we can give this input to, we can convert this input into a input for sat. So we convert it into a phi, a valid Boolean assignment, and we can do this using the Levin reduction, and this can be done in polynomial time. So we convert the input for a computing function f which belongs to hash p, we convert it into a Boolean formula phi, and then we input this to the hash sat oracle, and this gives us the number n, which is the number of satisfying assignment for phi, and this is nothing but the output for f. So as we have seen that Levin reduction maintains the number of solutions after transforming the input, meaning the number of uh, the number n, which is the number of uh, solutions for the problem f, is retained when we transform into an input for satisfiability. And because this also has the same number of valid assignments, we get n, which is the output for f. So in this way we can reduce any problem, any counting problem f which belongs to hash p to a hash sat problem. So hash sat is hash p complete. Now since we already know the satisfiability problem is NP complete and the hash sat is hash p complete, so is there a correlation between these two classes, and is there a direct mapping between these two, meaning are the NP problems uh, and the corresponding hash p problems, do they lie in the same way, in the same complexity, meaning all the uh, all the NP complete problems, do they turn into hash p complete, and all non NP complete problems, do they turn to non hash p complete. So let's find out if that's the case. So now we move on to the another uh, problem, which is hash cycle. So cycle the cycle problem in a decision problem, which is a decision problem which is concerned with, given a graph, we need to find if there exists a cycle in the graph. So, and this is a pretty straightforward problem, and we have a polynomial time um, algorithm which can solve this problem, and we can use depth first search for this kind of problems. And since it has a polynomial time solver, we can say that the cycle decision problem is in P. It belongs to the class P. Now uh, let's take the counting analogous of cycle problem, which is hash cycle. So what we are concerned with here is how many cycles are there in a graph. So given a graph, we need to find all the number of cycles. So this, as we see, is not a simple, there's not a simple way to find it, and it's a hard problem. Now one of the implications which is interesting here is uh, if we consider hash cycle is part of FP, meaning it's polynomial time function problem, then uh, this implies that P is equal to NP. Now to prove this, we need to first define a problem called Ham cycle, which is basically Hamiltonian cycle, which is basically a cycle problem, but we ask whether there exists a Hamiltonian cycle in a graph or not. So as we know, a Hamiltonian cycle is a cycle which uh, consists all of the vertices of the graph. So a graph of n nodes will, if it has a Hamiltonian cycle, the cycle would be of n nodes. So we need to use this problem in order to prove uh, the above implication here. So if hash cycle belongs to Fp, a function polynomial, this implies that Ham cycle belongs to P, which we know Ham cycle is an NP complete problem. So, and if we show that Ham cycle belongs to P, then we automatically say P is equal to NP because Ham cycle is NP complete. Now to prove this, what we do here is we take a graph G with n vertices, and what we want to do here is we need to construct a new graph G dash such that if G belongs to a Ham cycle, meaning if G is a graph which has an Hamiltonian cycle, then this is correct if and only if G dash has at least n power n square cycles. So let's see uh, how this is true, and to that let's define this graph G dash. So the trick here is to inflate the cycles of graph G in such a way that in the graph G dash the number of cycles n power n square can be reached if and only if G has an Hamiltonian cycle. So to construct the graph G dash, we use gadgets. So as we have already as part of our assignment used this to construct graphs in order to prove statements, so we are using a gadget here as well. So what we are going to do here is, if a graph G has a path from U to V, then in the new graph G dash, what we do here is we put two m vertices in between, and we have edge between all of them. So we use this kind of gadget to inflate the cycles from G. So every path from the graph G will have a corresponding gadget in the graph G dash. So as we can see here is, in a given gadget, the number of paths from U to V becomes 2 power m unique paths. So uh, each gadget has 2 power m unique paths. Now, so from this we can infer that, let's say a graph has a cycle of 3 vertices, meaning 3 nodes. That means it has 3 edges. So, and each edge in the graph G dash has 2 power m unique paths. So So it is basically 2 power m cycles. So for a cycle of length 3, what we get here is 2 power m cube number of cycles in the graph g dash. So let's see how we derive this. So here we see that g is a graph, and after using the gadgets we inflate it into a graph g dash which looks somewhat like this. And let's consider the graph G has a cycle length of L. This implies that the new cycles that are going to be added into the G dash is 2 power ml. So 2 power m is uh, the number of unique paths between u and v in the gadget, and since all of them unique paths, in the sense all of them define one cycle, so the new cycles here, because it's L edges, then it becomes 2 power m whole power L new cycles. Now let's consider if the graph has n cycle of length n, so meaning it has a Hamiltonian cycle. In this case, we see that the number of new cycles added would be 2 power m whole power n. And now we need to get to the value of n power n square, we can substitute m as n log n. So we derive this value according to the number n power n square that we targeted to reach. So that is how we get a number m in terms of n. So now here what we can see is, if G belongs to Ham cycle, meaning the graph G has a Hamiltonian cycle, then G has a cycle of length n, and G dash has at least n power n square cycles. So as we saw here, the number of new cycles added for this cycle of length n in G would be n power n square. So we have at least n power n square cycles. So we have proven one way around for this given implication, that if G belongs to Ham cycle, then G dash has at least n power n square cycles. Now to prove the other way around, meaning if G dash has at least n power n square cycles, then G must belong to Ham cycle, meaning G must have a Hamiltonian cycle. So let's take the contrary for it, and let's say G doesn't have an Hamiltonian cycle, and the largest cycle that it has is n minus 1. So L is less than or equal to n minus 1. Now this implies that the number of new cycles that are going to be added in G dash would be 2 power m whole power L, and L, since is upper bounded by n minus 1, this is less than or equal to 2 power m whole power n minus 1, and this would be equal to 2 power n log n power n minus 1. So after we calculate this, and we can write it in the form n power n square minus n. So if L, so these are the new number of cycles that are being added in G dash. So n power n square minus n, which is less than n power n square. So but it might have other cycles already present in the graph. So we need to make sure that even adding those additional cycles from the graph G dash, it wouldn't cross the bound n power n square. And so to do that, this is an important factor that we need to put in where the number of cycles in original graph G must be upper bounded by n power n minus 1, meaning the graph G cannot have more than n power n minus 1 cycles in it. So using this fact here, we can show that even adding the additional cycles from graph G dash, we cannot cross the upper bound of n power n square. So we show it by, let's say G doesn't belong to Hamilton cycle like we defined here, meaning the longest cycle of G is n minus 1. So L is less than equal to n minus 1, and G dash has, this implies that G dash has at most n power n square minus 1 cycles. So as we saw, n power n square minus n cycles is the newly added cycles. So, and we have also upper bounded the number of cycles in G by n into n power n minus 1. So if we say the number of cycles in G is the maximum of n power n minus 1, and all of them are of length n minus 1, then that is the maximum number of cycles in a graph which does not have a Hamiltonian cycle. That is the most number of cycles that you can get. And we can, so adding all these additional cycles as well would give us a value n power n square minus n into n minus 1. So this would be equal to n power n square minus 1 cycles. So this is how we get this. So this is again less than n power n square. So we have proven the other way around as well. So we can say now that if G belongs to Hamiltonian cycle, then this is correct if and only if G dash has at least n power n square cycles. Now this implies that the Hamiltonian cycle is solvable by hash cycle. So if we can solve the hash cycle problem, meaning we can find the number of cycles in the graph G dash, we can then solve Hamiltonian cycle as well. So this again implies what we are trying to prove, that hash cycle, if it belongs to FP, meaning as a functional polynomial class, then meaning it can be solved in polynomial time, then so can Ham cycle be solved in Hamiltonian time as well, which would imply that P is equal to NP. So this completes the proof for the given implication. And now one more additional fact which we are not going to go into right now is that hash cycle is also an hash P complete. So as we saw here is cycle, which is a P class problem in the decision problems, but in counting problems the so let us look at this diagram over here. So as we all know that P is a subset of NP, and P is also a subset of FP, which is the function polynomial, and we know that the NP complete problem of SAT has a counterpart of hash SAT, which is a hash P complete, and we also know that there is a P problem called cycle which has a counting counterpart called hash cycle, which is hash P complete. So here we can say like there is no direct correlation of hash P with any of these classes. So it is really different in that sense. So let us move on to another class here, which is known as PP. So PP is the probabilistic polynomial class. So it's a class of decision problems which are solvable by a probabilistic Turing machine in polynomial time. and which has an error probability of less than half for all the instances. So, so we can define this class as so any language L which belongs to this class PP, uh, if and only if there exists a probabilistic Turing machine M such that M runs for a polynomial time on all inputs, and for all x belongs to L, M outputs 1 with probability greater than half, and for all x which does not belong to L, M outputs 1 with probability less than or equal to half. So the maximum error probability would be half here. So similar to the case of such problems, even when studying counting complexity, we can often restrict our attention to decision problems, and the reason is that this class of PP, which is would imply an important fact that if PP, which is probabilistic polynomial, were equal to the polynomial class, then that would imply that hash p would be equal to the function polynomial, meaning hash p problems could be solved in polynomial time. So when we look at this picture over here, we can see where the class PP sits among other classes. So we can see P, which is polynomial, uh, which is a subset of RP, which is randomized polynomial, as we have learned before in the course, uh, which has co-RP, which are both a subset of BPP, which is bounded probability polynomial, and uh, this whole thing sits under PP. So we can show that BPP is a subset of PP here. So as we know, BPP, which is bounded probabilistic polynomial, it has a so with the probability greater than equal to 2 by 3, it gives us the correct answer, and with the probability of error is maximum of 1 by 3. So similarly in PP, as we have discussed, the probability of it giving a correct answer would be greater than or equal to half, and uh, the probability of error would be at most half. So we can see that BPP is a subset of PP, as we can boost this uh, probabilities to achieve this. So similarly, as we have studied, like uh, P, which is polynomial, is a subset of RP, we have used this argument where we can boost the probability for the randomized polynomial to solve the problems in P. Similarly, we can boost uh, the probabilities of BPP to solve the problems in PP. So, and we know that all of these classes sit under P space. So we have a definition over here, which is so if L belongs to the class PP and X is a string in this language L, then this would imply that the number of elements in this set which has y, a string of uh, length of polynomial of x, and such that m, a Turing machine, takes x and y and gives 1. So if m is a probabilistic uh, Turing machine and x is the input string and y is an output string, and if there is an accepting path between x and y, then we get a 1 here. So this is nothing but a set of all uh, strings which have an accepting path for the Turing machine M, and this is the total number of accepting paths. Now this number should be greater than or equal to half of the total number of paths possible. So for a string of uh, length polynomial of x, we have a total number of paths 2 power the polynomial of x. So half of these must be at least half of these must be the accepting paths. So we can think of it as PP is a set of problems that can be solved by a non-deterministic Turing machine in polynomial time. Sorry, M is supposed to be non-deterministic Turing machine here. So uh, so the set of problems that can be solved by a non-deterministic Turing machine in polynomial time, where the acceptance condition is that a majority of computation paths accept. So uh, more than half of the paths should be accepting paths. Now let us move on to another complexity class called parity P. So in complexity theory, the complexity class parity P is the class of decision problems solvable by a non-deterministic Turing machine in polynomial time, where the acceptance condition is that the number of accepting computation paths is odd. So as we know, the class sharp P is concerned about finding out the number of accepting paths, but in parity P we are just concerned about if the number of accepting paths is odd or not. So one of the examples for a parity P problem is, does a given graph have a odd number of cycles? So uh, so this is a counterpart for the hash cycle that we have already discussed. This is a parity P counterpart for that. Um, so parity P is a counting class and can be seen as finding the least significant bit of the answer to the corresponding hash P problem. So, so the corresponding hash P problem gives us an output which is a binary string uh, representing the number of accepting paths. So as we know, the least significant bit tells us whether the number is even or odd. So this reduces down, so parity P reduces down to just finding the least significant bit of the corresponding hash P problem. So lastly, let us discuss the complexity class called PH. So PH is a complexity class which is the union of all complexity classes in the polynomial hierarchy. So what is polynomial hierarchy means? We can consider uh, a hierarchy of classes where uh, each of the class is above or below in the hierarchy according to this statement over here. So delta I plus 1 p is equal to p to the sigma I p. Uh, so it is all the, so let's say this has an oracle, then all the problems that can be solved uh, using a polynomial reduction if we had an oracle for this. So what is this quantity, what is this class or this set of problems over here is, so sigma 1 p is np and sigma 2 p is p over np. So all the classes which so all the set of problems that can be polynomially reduced if we had a oracle for an np complete problem. So similarly we consider so I plus 1 to p is where we have a set of problems here, and if we have an oracle for these problems, then we have a uh, polynomial time reducible using that oracle. So this forms the set for such problems. Uh, so PH is defined as a union of complexity classes the in this polynomial hierarchy. So this is union of k, which is a natural number. So we have delta kp. So it starts from delta 1p union delta 2p union delta 3p. So all the problems that are uh, solvable all the problems which are a part of this set is comes under the PH class. So it is a much broader and a generalized class which contains classes like P, NP, and it contains BPP, RP, co-RP. Um, so one of the important facts about the class PH is uh, it is contained in P to the hash P. So PH would be a subset of this class P to the hash P. So meaning a polynomial reducible uh, if we have a hash P complete oracle. So which would be like P to the hash sat. So this is called as Toda's theorem, and this states that PH is contained in this set of classes, set of problems. So, and as we know that this PH also lies under P space. So I think we are good covering content in here because we have covered quite a bit of content. And Toda theorem is there is a proof for Toda theorem which is quite long, and it would require a few lemmas to be proven first. So we are not going to get into that now. So let us just recap once what all we have covered up to now. So we first defined um, decision problems, and what are function problems, and how are the counting problems and decision problems subset of function problems. And we looked at an example of a counting problem where we modeled a probability finding problem into a counting problem, and we defined the class FP, which is function polynomial, and then we looked at hash P. So we defined what is the class hash P, and we went through its uh, definition in the form of a relation. Then we tried to find or define the hardness of hash P. So to do that, we looked at two problems which are Hashsat and Hashcycle, and we defined what is Hashsat, and we showed that Hashsat is a hash P complete problem using the Cook-Levin theorem. We showed that, and we did this uh, reduction to show Hashsat is hash P complete. And then we looked into the Hashcycle problem, and we proved this implication that if Hashcycle belong to a function polynomial, this would imply that P is equal to NP. To do that, we showed if this would be the case, it would imply Ham cycle, which is an NP complete, would belong to P, and we used the trick of creating a new graph G dash in such a way that this property would hold, and we showed that this is indeed the case, and we proved that this statement that we had set up would imply that hash cycle, if belong to Fp, would imply that P is equal to Np. Then we looked into some of the other counting classes. So class PP, we defined it, and we looked it in terms of the other probability other classes like BPP and RP, and then we defined what is parity P and pH. So if you would like to read further on this topic, then you can go through chapter 9 from the Aurora textbook. And yeah, so I think that would be it for this lecture. I hope I was clear enough to follow, and yeah, thank you.